Welcome to this video on Fourier series, a powerful mathematical tool for representing periodic signals in the frequency domain. It forms a crucial foundation for modern signal processing and engineering. First, what is a periodic signal? It's a signal that repeats its pattern over a regular interval of time, t. Mathematically, this is expressed as x of t equals x of t plus t, where t is the fundamental period. Why use the Fourier series? It simplifies complex time domain signals by breaking them down into simple frequency components, known as harmonics. This is essential for audio processing, communication systems, and filtering, where frequency content is key. The core concept is twofold: synthesis and transformation. Any periodic signal can be synthesized as an infinite sum of sine and cosine waves. This transformation moves us from the time domain to the frequency domain, revealing the hidden structure of the data. Section 2 will focus on the concept and representation of the Fourier series, delving into its mathematical foundations. The trigonometric Fourier series represents a signal as a DC offset plus a sum of oscillating harmonics. This equation is the general representation for decomposing a signal into its constituent frequency components. The fundamental frequency, omega naught, is the lowest frequency component of the periodic signal, calculated as 2 pi divided by t. Every other harmonic in the series is an integer multiple of this base frequency. Harmonics are integer multiples of the fundamental frequency. The fundamental is n equals 1, the second harmonic is n equals 2, and the third harmonic is n equals 3, and so on. The DC component, A naught, is the constant term representing the average value of the signal over one period. Visually, it is the vertical shift or offset of the waveform from the horizontal axis. Section 3 covers the Dirichlet conditions, which are the essential criteria for the convergence and existence of the Fourier series. The convergence requirements include finite extrema, meaning a finite number of maxima and minima, finite discontinuities, where any jumps are finite in number and magnitude, and absolute integrability, ensuring the signal's area over one period is finite. Condition 1, finite extrema, ensures smooth behavior. The function must not oscillate infinitely fast. Most physical signals satisfy this, as they are energy limited. Condition 2, finite discontinuities, allows sharp signals like square waves to be analyzed, provided the jumps are countable and finite. Here we see a square wave approximated by a sum of sine waves. Dirichlet conditions are critical. They ensure the existence of the series, confirming that the Fourier expansion actually represents the original signal without divergence. They also provide numerical stability for computer simulations. Section 4 will explore Fourier coefficients, focusing on calculating the weights of each harmonic component. Calculating A naught, the DC term, is done by integrating the signal over one full period and normalizing it. This gives the average value of the signal. The coefficient A sub n measures the even content or cosine similarity of the signal at the nth harmonic. We multiply the signal by the cosine function and integrate over the period. The coefficient B sub n measures the quote content or sign similarity of the signal at the nth harmonic. This requires multiplying the signal by the sine function and integrating over the period. The role of the coefficients is twofold. First, relative weight. Higher magnitude coefficients mean that harmonic is more prominent. Second, shape information. The balance between A sub n and B sub n determines the phase and shape of the resulting waveform. Section 5 focuses on symmetry, a technique for simplifying calculations using geometric properties of the signal. An even signal satisfies x of t equals x of negative t, mirroring across the vertical axis. For even signals, only cosine terms, A sub n, remain, and B sub n is 0 for all n. An odd signal satisfies x of t equals negative x of negative t, rotating about the origin. For odd signals, only sine terms, b sub n, remain, and a naught and a sub n are 0. The advantage of using symmetry is calculation speed, as it instantly eliminates half of the required integration work. It also assists in intuitive design, helping engineers exploit symmetry in filter and system designs. Half-wave symmetry satisfies x of t equals negative x of t plus t over 2. The second half of the cycle is the inverted version of the first half. The result is that all even harmonics, n equals 2, 4, 6, and so on, are 0. A practical insight: always check symmetry before integrating. Shifting the time origin can often create symmetry in an asymmetric signal. Symmetric signals include square and triangle waves. Section 6 will compare the Fourier series and the Fourier transform, understanding their domain boundaries. This table outlines the key differences between the Fourier series and the Fourier transform across domains, signal type, spectrum, and applicability. The Fourier series is discrete, meaning information exists only at multiples of omega naught. The Fourier transform is continuous, where information exists at every possible frequency. Section 7 covers harmonics and reconstruction, showing how complex waveforms are built from basic components. In harmonic content, low-order harmonics define the general shape of the signal. High-order harmonics, on the other hand, add the fine details and sharp edges of the waveform. Signal reconstruction demonstrates this principle. By adding more terms, or higher-order harmonics, the synthesized signal approaches the original waveform with greater fidelity, effectively improving the approximation. However, attempting to reconstruct sharp discontinuities introduces the Gibbs phenomenon, a fundamental limitation. At these abrupt edges, the series exhibits an unavoidable ripple or overshoot that remains even with an infinite number of terms. Section 8 introduces a systematic approach to problem solving when applying the Fourier series. Step 1 is setup. Identify the signal type, determine its fundamental period t, and confirm the Dirichlet conditions. Step 2 is check symmetry. Assess for even, odd, or half-wave symmetry to potentially eliminate coefficients a0, a sub n, or b sub n. Step 3 is calculus. Apply the integral formulas to compute the non-zero coefficients. Step 4 is construct series. Substitute the computed coefficients back into the general Fourier series equation for the final result. Fourier series has vast real-world applications. It is used in audio compression like MP3s, communications for multiplexing signals, and medical fields for analyzing ECG patterns. In summary, key takeaways are: everything is a wave, meaning periodic signals are collections of harmonic components. Domain shift simplifies complex time domain problems. And finally, symmetry is a crucial engineering tool for efficiency. In conclusion, the Fourier series is a cornerstone of modern engineering analysis, providing the tools to analyze and synthesize complex signals. Thank you for watching this video on frequency domain analysis.